Hello everyone, today I am going to do a comparison between the 3D printed solids and our aluminum solids. So let me get this clear. I am in no way trying to diminish the 3D printed solids. It is a great design and an incredible way to make the designs accessible to anyone around the globe. Anyone can print those or have one of these printouts in their local 3D printer, and that is one of the reason that made the original Solix Direct so popular. This one made by thousands, I think. There are a lot of these out there, and they work pretty well for their price. So, but let's face it, there are some limitation with the 3D printed housing. That is why I was pushed to make a aluminum one. Now let's talk about some of the advantages as well as disadvantage of the aluminum solids. Well, first thing first, let's talk about the advantage of the aluminum solids. The first is the thermal stability. As you can see, those are printed from plastic, thermal millwork plastic, and those are not very thermally stable, meaning they will deform under high temperature. This one is printed from PLA, and that is a very thermally unstable material. If you put one of these under sunlight for 2 or 3 hours every session, and you put it out there a few sessions, you will have it degrade in a few weeks, and it will become very brittle, and the housing would crumble. You can take it out just by hand. That is with the PLA. It is not designed for outdoor use. So it has to be noted that there are some other material that was used to 3D print those, like the ones from Azure 3D prints. They made one of those from PETG, and most recently ABS, and those are very thermostable plastic, and I'm sure they have great performance. But for the V2 version, they have printed those from PETG. You still have to have some kind of shielding on the 3D printed one to shield them from solar radiation. You have to put some kind of shielding in front of it, and or wrap it around in aluminum foil, which is very unappealing. It's ugly to do so. With the aluminum solids, you don't have that worry. You can put this out there in day after day, and it will last a very long time. That is a guaranteed performance. One more thing is that because those are not thermally stable, it will deform under the solar radiation and the high ambient temperature. For example, in Vietnam, we usually have it's about 60 or even 70 degrees Celsius under direct sunlight, and those will deform under that extreme heat. Because of the deformation, the optical path will get deformed, and the geometry will get shifted, and that will result in a shifted focus of the collimator and the camera as well. So you will see after a season or two, If you use one of these in the remote observatory, that's what I'm doing, you will see the focus gradually change, and your image will become gradually out of focus. And that is the biggest reason why I went with the aluminum one. It is more thermally stable, and it will keep its shape, its focus, its collimation. Your focus, your collimation will just be what it is session after session, and you don't have to do refocus or any maintenance when it is on a remote setting. So that is the first thing. The second thing is the light isolation. One of the biggest problem with the original design is the light isolation, meaning the ability of the housing to keep light away. So as you can see, this one here, it has to put a tape on the side here. The original design doesn't have a light shield, and it is easy to have light leaks around the edge here. That isn't a problem with the aluminum solid. This is the first batch. On the second batch, we have a lid here that closes down from this side to this side, and it will completely eliminate the light leaks. Not that on the first batch it also have zero light leaks, but on the second batch we improved the design to incorporate a lid over the housing to further the light isolation. So no worry on that front. One more thing that the aluminum solid is superior to the 3D printed one is the thread performance. These on the 3D printed ones, the small thread here, they use some thread insert. It is brass thread insert. You heat them and then put them into the plastic housing. But if you are not familiar with the process, this can be very hard to do. If you're doing this yourself, you can put them at an angle, you can put them too deep, too shallow, and you can have them rip from the holes if you are over tightened those thread insert. So those are not very durable and very hard to put on. I've wasted maybe 3 or 4 housing, 3D printed housing before I can master those, and those are very hard to put on. One more thing is that for the aluminum, for the 3D printed ones, if you over tighten these, you will get deformed collimator or camera too. This one is deformed, you can see. I don't know if you can see on the camera, but with my bare eye, I can see it's deformed. It is slanted this way, and that is because the high temperature that this was experienced, and because of the tightening of the screw. You don't have that problem with the aluminum solids. One more one more improvement with the aluminum solids is the collimation process. For the other 3D printed ones, once you got the collimation by sliding in and out this collimator cube, you tighten one of those screws to set the collimator cube, to fix the collimator cube. And once you tighten those screws, the collimation focus will shift a bit, and you have to anticipate for that shift in when you do the collimation. You have to intentionally out focus the collimator. Then when you tighten the screw, it will come into focus, and that is a tedious and very hard process, very hard to master. On our aluminum solids, I fixed that. Now you just tighten this screw to fix the collimator cube, and it won't shift the focus of the collimator. I'll leave a link to the guide how to do so in the description of this video, so you can try that for yourself. So one more thing is the 3D printed thread. On the original design, there are two 3D printed thread on the Solex. The first one is this female T2 adapter, and you can see already here, those 3D printed thread is very hard to 3D print on your home 3D printer, and it's even harder to make those with the thermally stable plastic like PETG or ABS. This one is 3D printed from PLA, and that seems to be the only material I can 3D print those thread. Those thread doesn't work if I 3D printed from PETG or ABS. I'm sure that with engineering grade printer you can print those, but with home printer it is extremely hard to 3D print those and have them working correctly. Because of the low strength of the 3D printed ones, this telescope adapter here with the T2 thread adapter is one of the weakest link of the system, because it has to take all the weight of the system behind it. So this is a common place for failure. I see a lot of Starix Solex with this the failure here. That is not a problem with our Solex. All the threads are milled from aluminum, from aviation aluminum, and those are extremely durable. You can put a lot of stress on here and they will keep their shape, and they will do it for a very long period of time. One more thing about the aluminum Solex is that it has extremely high geometry precision. Our Solex, aluminum Solex, has a tolerance of about 0.05 millimeter, while the 3D printed ones generally have a tolerance of about 0.2 to 0.5 millimeter. That's an order of magnitude better than the 3D printed ones. With better geometry precision, you will have smoother and more precise movement, such as the rotation. Here you can see it is rotated very smoothly, while on the 3D printed one, when you rotate this, the center of rotation might shift a little, and that shift will show on the spectral on the camera. The spectral line will go in and out when you rotate this ring. That is not a problem with this Solex, and it is a huge improvement to the experience of the Solex. So to recap, the advantage of the aluminum Solex in comparison with the 3D printed one is the first, thermal stability and durability. Secondly, the rigidity of the aluminum. Third, the thread performance is superior, and fourth, the geometry precision and the smoothness of movement of those parts. So those are the advantages. Now let's talk about disadvantage. The first obvious disadvantage of this aluminum housing is the weight. This one is significantly heavier than this one here. This one here weighs maybe about 400 grams or so, and this one weighs about 1.1 kilogram without the optics. So with the optic, the focuser, it will be about 1.3 or 1.4 kilogram, and that is a significant increase in weight. So as of my recommendation for this, you might want to have a for example, if I put this on the telescope here, you can see it is very stable. But if you want to keep the focuser from drooping from all the weight here, I recommend you to put on a push-up screw like this on the end of the Solex. So these put-up screw will help the counteract a part of the weight of the Solex and make the system stiffer, less vibration, less resonance, and that will help you take higher quality images. It is recommended to with the Solex to have some kind of support here on the Solex, since it is used outside under sunlight. It is recommended to have some kind of support here to minimize failure at the telescope interface and to keep the system straight. Now, okay, that is everything I have to say about our Solex aluminum kit. If you have any question, just leave it in the comment down below. See you. Bye.